Fairly cool. Canberra night. You recording?
As quick as we can.
Go. The joys of technology. Well, welcome. Welcome, and especially my friends from the department. I'm pleased you could make it. So tonight I want to talk about radios and satellites. This is a revised and expanded talk which originally I gave at GippsTech in July this year. I've expanded it a bit because of some recent events, and I only had much more limited time there, so I had 20 minutes, so I'll have a bit more than 20 minutes here. So anyway, the title, as Wade is, I can't see this keyboard now. So I stole it from Wind in the Willows. There's nothing, absolutely nothing, half so much worth doing as messing about with radios and satellites. It's a variation on what Kenneth Graham said in Wind in the Willows, because I reckon it's true. Anyway, so most of you are aware that there's a large and active community of amateurs across the world who are interested in satellites, use them for various things. So we use them for communicating with other amateurs. There's also quite a lot of interest in collecting telemetry from amateur and amateur educational satellites. And this will really be the focus of my talk tonight, about reception of telemetry, because I've spoken before about communications. So the reception of telemetry is interesting in itself, but it's also a service to the wider community because the data is sent to an end user. And I'll explain all of that in a minute. So, but first of all, what are amateur satellites? So, an amateur satellite provides two-way communications. They usually operate in low Earth orbit between about 400 and 1100 kilometres. Notably though, we now have this satellite here, Eshale-2, or QO100, which is in a geostationary orbit over the Middle East. So that's the first geostationary satellite that amateurs have access to, and it's actually a couple of transponders on a commercial satellite, but it was organised by the Qatar Amateur Radio Club with some help from commercial interests. So ordinary amateur satellites can be of a number of sorts. They can be a single channel FM repeater that we're used to terrestrially. They're commonly called bent pipes. What goes up comes down. There's linear transponders, which are a bit more complicated. They're good for single sideband and digital applications. So in which case they have a much broader bandwidth. You can have multiple channels, multiple conversations or multiple applications occurring at the same time through the same satellites. They're technically much more complicated and you need a more elaborate ground station to use them. Some satellites also have store and forward messaging, so you can send an email to it up here and somebody in the US or Europe can download it. And also APRS, that stands for Amateur Position Reporting System. So that reports the satellite position or relays people's terrestrial position by a satellite. The International Space Station has carried that capability for years, and there's probably another half a dozen satellites which also serve a similar purpose. And then you can go to a map on a website somewhere and find out where people are, where you are, where the satellite is. We've had amateur satellites since 1960. AO1 went up just 3 and a bit years after Sputnik 1. Australia was involved very early at RMIT. They built AO5. That was launched in sometime in 1970, and it was the first satellite that had any sort of remote control capability, and it was stabilised. It used magnets to stabilise the attitude. So that was really a first for Australia. You may not have heard of amateur educational satellites. However, they're increasing. There's a lot of them going up and being launched. So they're built by universities, high schools, some companies for very specialised applications. Primarily they're used for training of students at university or high schools. Some universities, particularly in Europe, run courses for graduates. Their project for the year is to build a satellite and get it launched. And some universities are very successful in that, particularly the Technical University of Berlin. They've done it for about 9 years in a row. So they've had VSAT 1 and it's now about VSAT 9. Often they don't have any two-way communication capability. They carry some sort of science experiment or some sort of educational facility. So some of them in particular are very STEM oriented. So STEM is science, technology, engineering and mathematics. And to get a satellite launched you need a lot of all of that to make it happen. So they're a terrific educational resource. If they're operating in the amateur band, they have to be open access, they can't use encryption, all of the information has to be available for amateurs to use them. And typically, if they're licensed for use in the amateur band, somebody in the organisation will have an amateur licence. Nearly all of them are what they call CubeSats, and we'll look at CubeSats in a minute. So what's a CubeSat? Well, it's a small platform. You can go and buy one off the shelf if you've got enough money. Not very much money. $100,000 will get you a really nice one. CubeSat is about that big. That's a 1 1/3 CubeSat because the basic size is 100 millimetres by 100 millimetres by about 100 millimetres. Roughly 1 litre, so it's roughly that size. That is the smallest CubeSat, and there's lots of 1U CubeSats in space, and they have some remarkable functionality. The next most common size is 3U, then there's 6U. And you can buy all of these bits commercially. Some people build them themselves, but if you just want to get one, you can go and buy the frame, the computer, the comms capacity, and put it all together. Lots of people do that, and it goes no further, because if you want to get it launched, it costs you a lot of money. Roughly $100,000 per kilogram to get it into space. So a CubeSat that size, roughly 100,000 US to get into space. But they're very popular. So I said there's lots of them going up. How are they regulated? Obviously you need some sort of coordination, otherwise they're going to cause interference to other satellites and ground services. So under an arrangement with the International Amateur Radio Union and the ITU, the IARU frequency coordinates satellites to minimise interference between satellites and terrestrial services. As I said, if they're going to operate in amateur bands, they must have some amateur application. It doesn't have to be communications, but definition is quite broad if it has some aspect of radio technique. So that could be attitude stabilisation or some communications modes or something of interest to the amateur service or some relevance to the amateur service. They will generally be coordinated. And there's satellites doing propagation studies, again science, technology, engineering, mathematics, education. The field is quite broad, and generally a satellite will get coordinated, but there are satellites that don't fit that classification because some administrations launch them anyway. So there's a number of threats, and they continue to evolve. But mostly people play by the rules. So that's a bit about the background. Now I'm going to talk about receiving telemetry because it's quite an interesting activity in its own right, and there's a lot to learn. And there's lots of birds to hear, so birds being shorthand for satellites. And I'll focus on, in the first part, the Fox class. So the Fox satellites, that's AO 85, 91, 92 and 95, they transmit relatively slow speed data under voice. They're FM satellites, and you just hear this burbling away while the satellite's active, and you can get the telemetry from that, gives you the satellite health, some other information, details on the experiments on board, and the data you collect is then sent back to what's called the data warehouse, the organisations who want the data. Second class I'll talk about are fun cubes. So the Fox class are typically have come out of America, North America. The fun cubes come out of England basically, but they've sold some of these things to other countries like Jordan and UAE. So some of those countries also have them, again operating under the amateur service. So stations aren't particularly complicated, basically need a receiver, an antenna and some software, and you collect the data when the satellite's flying over top, and the software processes it and streams it to the warehouse, and that's a service that we can provide to the wider community. So here's a picture of the CubeSats. So this is Juliet Oscar 97, that's operated by the Jordanians, and that's AO91, which is operated by the Americans. Both have science experiments on board, but both ultimately will have communications capacity as well. They're both 1U CubeSats. As I said, the Fox-class satellites are built by AMSAT North America and in conjunction with a couple of different universities. Their primary communications payload are FM repeaters, so people use them to talk to one another. They're at a reasonable altitude, about 500 kilometres. So with that, it's very easy to talk from here to New Zealand or here to Perth. Some orbits, maybe New Zealand to Perth for a short period of time. So they're quite a good satellite. They have other payloads as well. In the case of the Fox satellites, they have particle counters for looking at the radiation environment of space. One of them also has a camera for doing Earth observation, and I'll look at another example of that towards the end of the talk. Space is a pretty tough place, so not all the satellites work all the time, but AO91 and 92, they're fully functional, the repeaters are working, the telemetry is working correctly. They both are very heavily used over Australia. Pretty much any time they're within sight of your ground station, you'll hear somebody using it. So they're quite active, both with voice and slow scan TV. And there's been quite a lot of slow scan TV activity lately. AO85 and 95 are partly functional. AO85 is pretty much deaf. It was damaged before launch, and AO95 got up there, it's transmitting, but it's totally deaf. They can't control it. It's just sending periodic telemetry, so that was a disappointment for everyone. You don't need much to listen to them. You need a radio, obviously. I use this particular one. It's a software-defined radio. It's about the size of a cigarette packet. It's a terrific receiver, not terribly expensive, and it works exceptionally well. You need an antenna. I just use, in this case, an omnidirectional antenna, just a half-wave antenna with a low noise amplifier at the feed point and a computer to decode the data. To make it all work, though, there's a bit of work necessary to sort of glue it all together. Tracking software. The only reason you need tracking software is to adjust the frequency of your radio to compensate for Doppler shift. There's the software which talks to the software-defined radio. You need the telemetry decoder. Then you need some what they call virtual cables to link it all together. So in the past, you might have had all these different modules and you had a rat's nest of cables at the back of your computer. The way of doing it these days is you use software which looks like a cable. And it works mostly pretty well, although there are some traps which I'll talk about in a while. So there's the block diagram. A whip antenna, low noise amplifier, which is fed DC up the coax. I put a bandpass filter in because in Canberra at least where I live, 2 metres is quite noisy. And so that tends to, if I don't put the bandpass filter, it tends to overload the front end of the software-defined receiver. I split it in 2 ways. I use a standard receiver as well as the software-defined receiver, because when that's running, I get a waterfall display of the whole band. And occasionally there's other satellites pop up that I'm interested in, that I want to listen to, without disturbing the main telemetry channel. So I can, with the other receiver, listen to any part of the band. And occasionally you'll see 4 or 5 satellites that are visible at the same time. So that's been quite a useful station. That runs continuously and just sends the data as it collects it. Usually I get, there's probably half a dozen or maybe even 10 good passes a day for the 4 satellites, and all of that data goes to a data server somewhere in the US, and they take the data from the science experiments and the satellite health and put it onto a web page so everyone can access it. And there's a whole lot of people right across the world. They've got a web page which lists all of the stations and how they're doing, and there's probably 1,000 stations there that are contributing data. So that's an important part of the background. So it does work very well. As I said, the software-defined receiver is a 14-bit device. It's really very sensitive, although it's a bit prone to front-end overload. I talked about the separate receiver. I was really surprised how well the simple antenna, just the vertical, and the low noise amplifier works. So this is a plot of satellite elevation versus satellite azimuth. And as you'd expect with an omnidirectional antenna, the signals are coming in from everywhere. Of course, I'm not getting much from right at the top, even though there's satellites occasionally pass right over the top. The antenna has a deep null at the top, so that's showing up that I'm not getting anything much about it above 80 degrees. And you can see a clear asymmetry too. So I'm actually seeing, I get a better radio horizon towards the west and the northwest than I do towards the east, which is a bit curious, and I think that's because there's a tree there. so if I get the chainsaw out, I could probably fix that, but no, I've got limited space, unfortunately. So anyway, but the software provides that sort of analysis facility and a lot more, but that's a particularly good one.
How is it working out the direction?
Because the software knows where the satellite is.
Okay.
The Kepler elements.
Of course.
So I talked about the software. Again, all this stuff is freely available. You can download this, what they call dashboards. For the Fox satellites, it has a number of you can select which satellite you want. It gives you the data, shows you what the signal quality is like. But if you click on each tab, you'll get all of the satellite telemetry. It's satellite health, what the battery voltage doing, its temperature, its attitude, a whole lot of stuff about the data, and all of that gets sent back to the server somewhere. So here it shows I've sent 65 frames, 28,000 packets or something. So all of that just runs continuously in the background, and it all just happens. It took a while to make it just happen, but now it just happens. Talk about FunCubes. So this is the other side of the Atlantic. It grew out of the Surrey space, well, actually grew out of the University of Surrey. It's now a commercial company producing satellites of all sorts, but they produce these FunCubes, and they're specifically designed for education, so science, technology, engineering. AO-73 is an excellent satellite. There's a whole suite of experiments that it does, thermodynamics, orbital dynamics, various other things. But what's more, they provide a whole set of teacher resources so that you can get the data from their data warehouse and you can get your students to analyse it, how the satellite's tumbling, how it responds to solar radiation, all of that, that's all there, and the data warehouse is essential for providing that useful information for the students to analyse the information.
How long do these remain in orbit?
AO-73 has been up for about 5 years now, which is quite surprising given its relatively low elevation. It's a very reliable satellite. It's just there all the time, and it's quite a strong signal. Well, strong in satellite sense anyway. Not all, as I say, there's been a few of them. FunCubes 2 and 3 are dead completely. No one's heard of them for a long time. They're just gone. They're still up there, but they're not responding. FunCube 4, I know it's there, but there's no details on it, and that was, I believe, a joint venture with the European Space Agency in some sort of educational program, and whether that will eventually come good, I don't know, but there's not much information on it. FunCube 5, it was also known as EO-88, that's owned by the United Arab Emirates. That's again a very good satellite. It doesn't get much use in terms of communications, but it does have a lot of telemetry information, which is again collected by people and sent back to the warehouse. Juliet Oscar 97, FunCube 6, again built by the same people, is quite a recent satellite, and it's unusual in that it is really the next generation of these things because it has digital voice capability and some SSTV, slow scan television capability. which I'll show you in a minute. But it's not a happy satellite. It's supposed to have eventually a transponder, but that's not been activated, and I think I know why. Now, I'll tell you about that in a minute. For fun cubes, a similar setup, although I use a standard radio. Because the signals, you need a better signal to noise ratio, I use a 3-element antenna, 3-element Yagi antenna, and it tracks the satellite. The same software mostly, although I've got some controlling software to control the antenna position, which is written in LabVIEW. So here's the block diagram. 3-element Yagi with an antenna with a low noise amplifier. There's a rotator, and because I was cheap and used a second-hand TV rotator without an indicator, I needed to know where it was pointing, so I had to build a compass. So I know where it's pointing. That comes down through a network connection back to a PC. The signal split again to something, which I haven't decided what, but an FT817 and another PC, so just a free second-hand laptop that I got. And that again is another standalone station. In principle, that's a two-way facility, which I might develop a bit further as time permits. So it's fairly straightforward. Now going back to the software, so again we have dashboards. You can download the dashboard for each satellite from the relevant web page. At this point in time, there's multiple dashboards for multiple satellites, and you can generally run them in parallel on your PC. The ultimate aim is to have one for all satellites because the format of the data is more or less the same. The transmission protocol is the same. So in principle, you could have a single dashboard. And it gives you the satellite health, so it talks about the antenna, the transmit power, the radio, how that's going, amplifiers, the solar radiation on the panels, the temperature, everything about the satellites. Down here you've got a little display which shows you the spectrum of the received signal. They're a bit more complicated to use because on the Fox satellites they're FM, so you don't have to worry about Doppler shift, whereas these ones you do have to worry much more about Doppler shift. Your frequency has to be within a few hundred hertz, otherwise you get nothing. So the setup's a bit more finicky, and the software has to be a bit more particular about tuning the radios. But having said that, it's not too bad. So that's the antenna. I rotate in azimuth only. I just fixed the antenna at 45 degrees. That seems like a good compromise. Most passes are between the horizon and 90 degrees, so all passes are between the horizon and 90 degrees, so 45 degrees seems like a reasonable compromise. But well, ideally you would have, but in practice it hasn't been. For voice communications, yes, I use circular polarisation for voice, but for this one I don't. So for voice I've got a much more elaborate antenna with circular polarisation. However, to do this you need to know where the antenna is pointing, you need to know where you want it to point to, and you need to move it. So you move it with the motor at the bottom, the compass at the top, a little magnetic compass thing which goes for Arduinos, tells you which way it's pointing. The software knows where the satellite is and then moves the antenna to the correct azimuth at least.
So that magnetic sensor,
Sorry?
you don't have any interference from the other one?
Well, if it's... No, like you have to calibrate it, so you calibrate it in situ. And given it's only 3-element Yagi, your beam width's quite wide anyway, so you don't have to be within a degree or two. Probably 10 degrees is good enough.
Wouldn't a TV antenna rotator assume that you might move it once a week or something, rather than continual tracking multiple times a day?
Yes, but it hasn't failed yet.
Okay.
So how long is it passing minutes?
About 10 minutes. And I only move it about every 5 degrees, so it's like because of the wide beam width. Yes, so you don't need high resolution to be on. Not for these, you don't need high resolution. So as I said, a compass and an Arduino that talks to the PC, which controls the rotator. That's all pretty straightforward. it seemed at the time, but it didn't work very well. Took me a while to figure out why. The compass is a remarkable device. It's tiny. It's a tiny little device on a circuit board, not very expensive, and the specs say good to a degree. Okay, fine, I'll put it in. Didn't work, it was hopeless. It took me a while to figure out why. So I did some, so this is just a full 360-degree scan, rotation, monitoring the two outputs, the X and Y output from the compass. The shape's right. There's two things evident. There's an offset, which could be because it's near metalwork. And what's worse, there's a difference between the amplitudes. So, that's why you don't get very good results out of the box without calibrating it. The end result is this. Uncalibrated, the angular resolution is hopeless. It's unusable effectively. So the offset causes this big offset in positional, and then you've got this funny shape. So that wasn't terribly useful. However, if you scale the two sine waves and match the off and remove the offsets, it's a straight line. It's within a degree. It's very good once you're aware of that. So you have to calibrate the compass. That was the bit that was, that's the bit no one tells you about. When you do that, it works very well. Now the calibration is going to be different for each situation, of course, but it's easy to do. You just spin it round for 360 degrees, record it. It's quite straightforward, but it is necessary.
Is it fairly stable? So once you've collected the corrections, then it's...
Yeah, it's certainly good enough for this application. I mean, I would expect some temperature effects, but they're tiny compared to all the other errors in the system. So this is what the user sees. This is JO97. That's its footprint. Its elevation is about 600 kilometres. So that's the footprint there. When it's over Australia, you've got very good coverage. So this runs on the laptop. This software talks to this controlling software which controls the motor. So this software here, written in LabVIEW, it reads the compass and gets the commands from the tracking software and then moves the motor to the appropriate heading. And that all happens by magic, more or less. And then underneath is the dashboard for the satellite, which takes the audio output from the radio through a sound card interface and demodulates it. That all just runs on a laptop, runs continuously. It works beautifully. Really pleased with it. So we get excellent copy right across the path, usually 100% of the packets. You usually get around about 130 packets whole path, horizon to horizon. You get the telemetry, and as I indicated before, JO97 has some interesting features. It transmits pretty pictures. It's a whole series of pictures it transmits, and digital voice. So you can listen to the Crown Prince of Jordan in English saying greetings, which is, that's all it says. But it works, and it's a terrific educational resource. Now, as I said, I don't think it's a happy satellite. This is the telemetry. Data collection, failed. Antenna, 91 degrees C, undeployed. Things are disabled. I think there's a problem with the PA stage because the forward power is 47.77 milliwatts, the reverse power is 47.77 milliwatts. I think there's a problem with the antenna. And there's unknown resets and there's faults. So it hasn't been commissioned. It's transmitting telemetry, but so far it hasn't been commissioned for regular use, and I doubt that it ever will be, given that telemetry. Which is a bit of a shame, but it... My friends at the university who are involved in satellites reckon that 9 out of 10 satellites either fail are dead on arrival or fail very soon afterwards, and I think they're right. There's lots of dead ones up there. So,
is the telemetry all standard data formats, or is it all...
It's different for different satellites. But for amateur satellites, it has to be available somewhere. So generally there's a website somewhere that if you're really interested in doing it yourself, you can. It'll tell you what the protocol is and the encoding and error correction, all that sort of stuff. So that information, for it to be licensed as an amateur satellite, has to be available, open access. So what were some of the issues? Well, compass accuracy, solved that through calibration. Interference was a proper pain because I had right beside the antenna feed point a microcontroller and a network. That gave me some grief. That had to, so lots of screening, earthing, chokes, and Cat6 cables. Cat6A cables are great, double screen, they're beaut. Expensive, but they get rid of your, largely get rid of your interference. The software, again, was more or less okay. I was puzzled why, when I was running this, my laptop was running like really slowly. And it turns out that the server within the SAT PC32 software needs a response from the controller, and I hadn't put that in. So it was sending out a position, but it was waiting for acknowledgement, and I hadn't put that in the code. And when I did that, it became much happier. So, I mean, it ran, but it didn't run very well. Until I put that in, I had no idea. And it took a bit of head scratching to figure out what the heck was going on, but I eventually realised it. The virtual audio cables are great, but you've got to have the same sample rate in as you have the sample rate out. It doesn't work real well if you don't, and that is a trap. No one tells you these things, you've got to learn them yourself. So I talked about cables, I'll probably skip that, that's not particularly interesting, but the virtual COM ports let you transmit data from one application to another. It looks like a standard cable. You configure it like a standard cable, but it's a piece of software. Similarly for the virtual audio cables, they work well, and there's different ones available, some free, some you pay for. I'm just using free ones, but you've got to get your sample rate right. Surprisingly, it doesn't seem to matter for the virtual comms cables, but it certainly matters for the audio cables. LabVIEW, I use LabVIEW professionally for work, and it's really great for building control systems. It's usually very expensive. My previous employers have paid thousands of dollars for LabVIEW, many thousands of dollars, but you can get the student version for $50 US, which is excellent value. And providing I don't use it commercially, it's there, it's terrific. Let you have all of the usual programming constructs, but you basically draw a circuit diagram. And it's easy to use. It generates really pretty control panels, and it's a terrific program for this sort of application. I use it professionally for video processing and real-time video acquisition, so it's quite high performance as well. Now I've built all of this myself, but there is another way. There's an open source system run by a group called SetNogs, which is a funny name, but I'll explain it in a minute. So it's a group of people, I suppose it grew out of the Maker group, who wanted to get interested in satellites, and what they've done is put together a network of what they call open ground stations. So SetNogs is Satellite Network Open Ground Station. It's a network of stations focused on observing telemetry and signals from low Earth orbit satellites. The idea is that you can have multiple satellites throughout the world, and if you, as somebody interested or a researcher, can coordinate all of these different ground stations and get more or less global coverage. That's the plan. So each station uses the same or similar equipment, generally fairly low cost, although you often need a 3D printer to do it. It's all open source, community participation. I don't know how it's going. It'll be interesting to see how it's developed. The website hasn't changed much. So there's other aspects. So the International Space Station, which I saw last night, it was incredibly bright. Must have been a very good pass. It was just this thing going across. It has a lot of amateur radio equipment on board. Lots of astronauts are amateur radio operators, and they use it for backup communications. When other links go down, they can always talk to somebody on Earth using the amateur radio system that's on board. And there's this group called ARIS, which is Amateur Radio on the International Space Station, You've probably heard about that, but they organise links between the astronauts and schools around the Earth for kids to talk to the astronauts while it's flying over. And that's immensely popular and really good outreach between NASA or the space station, that whole organisation, and the community. So it's very popular. It's quite commonly done in Australia, but right around the world. They, a few times a year, perhaps half a dozen times a year, start transmitting images from usually the Russian section, and they transmit all sorts of images. It's quite easy to receive. It's a 25 watt transmitter. It's a strong signal on Earth, and the space station's only 400 kilometres up anyway, so it's a strong signal. And they'll just send lots of these images, and that's just a sample of them, and that is very popular. However, in recent times, in the last month or two, there's been quite a lot of activity using transmitting and receiving slow scan TV via the Fox series satellites. They're two-way, so I can transmit an image and somebody in New Zealand can send an image back, and in the 10 or 15 minutes you've got, you can send a few pictures. So the other weekend, there's a whole bunch of people, including me, sending images via the Fox satellites. It works really well. And depending upon the transmission mode you use, the quality can be quite high. I use my standard ground station. There's a few sort of tweaks and things you've got to do to make it work properly, but it works quite well and it's quite interesting. But now this is brand new. There's a satellite which was launched earlier this year. It's called NO-104, and it's built by the US Naval Academy. It must be a remarkable organisation because they have these things called short fuse launches. So somebody somewhere says, we've got a space on a rocket that's going up, have you got something to put it on? The US Naval Academy says yes, and they must have a room full of satellites just ready to go. And they can go and grab it, put it on, and up it goes. So, and I think they must build one a year for students. And most of them don't get launched, but some do. And this one is quite new, and what's new about it, aside from the fact that it's only gone up in the last few months, is that it actually has a camera on board which is pointed at the Earth, and it transmits real-time images of the Earth. It's not high resolution, but I received one this afternoon which was unfortunately had some interference on it, but you could actually see the outline of the east coast of Australia, which is quite nice. So here's the limb of the Earth, the sun coming up. There's another shot looking across the edge of the Earth. You can't see much, but it's pretty interesting. And no doubt as technology improves, the resolution that these things have will improve. And in fact, it's in some countries, particularly the US, these people had to get a waiver because in the US, anything that takes a picture, the US and Canada, anything that takes a picture of the Earth and sends it to Earth needs to be encrypted. And that was going to stop this satellite being launched. However, they got a waiver from the US administration to launch this satellite. So this is, that was an interesting wrinkle on this particular mission.
Dale, there was a fellow who was a senior technician at the US Naval Academy, Bob Bruninga.
Yep.
He's also the guy who invented APRS.
That's right.
And I think that it was his influence that got a lot of this program going over there.
Well, that's true, and he's still involved.
Whether he's still there, I haven't heard of him for years.
No, he's still there.
He's still there.
I emailed him with some photos. I said, here's some pictures from your satellite. And he said, oh, great. So, yeah, he's still there.
Wow.
Yep, he's still there. And he's got a lot of connections, and that's how he can find these short fuse opportunities.
Yes, he does have incredible connections.
Yep. So just as background, in the early days, amateur satellites would go up basically as ballast. So the rockets would go up, they didn't have a full load they weren't loaded to capacity, and they'd say, oh, well, okay, we've got some space, we'll put on an amateur satellite for free and set it up. Those days have gone in general. Basically, there's more demand than there is supply of of launch opportunities. So getting a satellite launched is now much more complicated or expensive. But because if you've got connections, particularly in the US military, I guess you can get stuff done. So here it is. It's an unusual satellite in a number of ways. It's almost, well, most amateur satellites are polar orbits. So they orbit north to south, and as the Earth rotates, the satellite covers the whole Earth. This satellite has only a small angle, low angle of inclination to the equator. So it's more equatorial than polar, which means that that's about as far south as it comes. So it's between, about plus or minus 35 degrees, which is quite unusual for an amateur satellite. And it's the only one I know of that has such an equatorial orbit. The only one that comes close to that is the International Space Station, which goes down to about 60 degrees, but this is unusual. The second thing that's unusual is that it's got a number of different modes on it. So it's got a PSK31 transponder. So PSK31, as you know, is a digital data mode. What's unusual in this case, it goes up on 29 megahertz and comes down 70 centimetres FM. So it goes up SSB and comes down FM. Has a digipeater for APRS. For what I was just showing you, it has a camera. There's a camera in there. And it takes pictures, and eventually I believe this will be on demand. So if you're interested, send it to command and it'll take a picture of you waving at the satellite and send it to you. I hope that happens. That'll be a lot of fun. So that's more or less a 2U CubeSat.
So this must be stabilised, so you know which way they're pointing, otherwise it comes to useless.
Yeah, well, some of the images look out into space. I only showed you the good ones.
Take a photo of an alien's way back.
Well, when I sent to Bob Baringa, he said, "Oh, nice shot of the antenna," because there was nothing else. All he could see was the whip antenna.
So what's the coverage of that?
What do you mean, the coverage?
So every space station can see that?
Yeah, well, this is the footprint there. So that's me there, the white dot or the white cross, and that's the satellite, the sub-satellite point there. So its altitude is, well, that's the other interesting thing I haven't written. It's in a fairly elliptical orbit. Most of the amateur satellites are in circular orbits. This is quite elliptical. Its perigee is about 400 kilometres and apogee is about 900. It's quite an unusual satellite in many respects. And that probably reflects the launch opportunity. So, it went up on some strange mission. So the footprint on the Earth will change depending upon where it is in the orbit. So, in conclusion, satellites, if you want to mess around with radios and satellites, it's a great opportunity for experimentation, technology development and education. You don't need to spend a lot of money. I don't. I try to avoid it at least. Well, my wife won't let me. So that's always safe. But you can use a lot of stuff that's readily available. You don't need to spend much money. So you can listen, look, but it's important that when the opportunity is there, that you actually use them to communicate, because that's the prime purpose is actually using to communicate with other people. And here, we're lucky we don't have a big density, so you can nearly always get time on a satellite, talk to somebody, and the satellites that are up there have terrific coverage, Australia, New Zealand, parts of Indonesia, Antarctica. So it's a terrific thing to do. I enjoy it a lot. So, that's it. Any questions?
Somebody said I'll spin one up tonight and see if there's an image ready to go. I've got a slot there ready to go.
Okay.
On the disco.
Great.
Perhaps it's about 10 minutes. How long does it take to download one of those images in slow scan?
It depends on the mode, but using these, if I go back,
You must get a lot of half images if they take a long.
no, they don't. They're only probably 20 seconds.
Oh, okay. So it's quite small.
And does it repeat, sort of keep repeating it so that you can, no?
Not this one. These ones are, 20 to 30 seconds, and once the image is gone, it's gone because the satellite's moved on. So you'll get something else next time. But it does have some stored images too, so occasionally you get a picture of the camera was built by the camera system was built in the Czech Republic. So I've received some nice pictures of what the camera looks like. So they're stored on board, obviously. So it transmits real-time images as well as stored images. These ones here, though, they're quite high resolution, so they take about 2 minutes. So with the space station, you'll only get 2 or 3 images and it's gone. But they're 380 by, they're 380 by, I forget what it is, but anyway, they're quite high resolution images. They take a couple of minutes to transmit.
I've seen guys just decode those with their phone, a HT and a Yagi on a tripod. There's software that does it, hold up your brain.
Yep. You can do that. Because it's quite a strong signal from the space shuttle. It's, say, a 25 watt transmitter, and whereas most of the other ones are only fractions of a watt, so that's fairly straightforward. But it does help to be able to track. For these, I actually track the satellite properly at altitude and azimuth, and have a bit more sophistication, because it does require a little more effort to get good quality images for those sort of that sort of resolution. Some of them are pretty much photograph quality. Occasionally you'll get photographs of the inside of the space shuttle, or what it looks like looking out the window. Sometimes you'll get pictures of that, or there's a whole series of history of Russian space flight from Yuri Gagarin on. They seem to have themes, depending upon what they want to do. But that's quite interesting, and that gets a lot of interest throughout the world.